Hi there. Welcome to our notes on 2-10. In 2-10, we're going to be taking a look at energy changes that accompany chemical reactions. Previously, we realized that to change the state of matter, to go from a solid to a liquid, we have to add energy into the system. It's endothermic. To go from a liquid to a gas, in other words, we want to boil something, we got to add energy into the system. Endothermic. If we have a liquid and we want to freeze it, we've got to pull energy out of the system. Energy has to move from the system to the outside. That's exothermic. When energy moves from the thing to the outside, it's exothermic. If we have a gas and we want it to condense back to a liquid, we've got to slow down the molecules so that they can get close enough to each other and pull back together. To slow them down, to lower their temperature, we have to remove energy from the system, the thing that we're trying to condense, back out to the surroundings. Pull energy out. That's exothermic. Well, energy changes, as we've learned, also accompany chemical reactions. We know that a strong evidence that a chemical reaction is occurring is a change in energy. Some reactions give off heat energy to the outside. They're exothermic. Other chemical reactions pull energy from the outside in. Those are called endothermic. When we're looking at the changes of energy that accompany chemical reactions, what we're looking at is one of the two driving forces of chemical reactions. There are two driving forces in chemical reactions. One of them is enthalpy. It's the measurement of the energy change overall, generally in the form of heat. Energy change overall. Now, the energy will often come in certain phases. It always takes energy to break the reactant molecules apart. That's energy in. It will always take energy in to get a reaction going. But once the reaction's going and we've broken apart the reactants and they're finding other things to chemically bond to, that step they release energy. So energy in chemical reactions come in two steps. Energy in to break it out, break them up, and then energy out as new bonds are forming. If the energy in to break the bonds is more than the energy that's given off when new bonds form, it's going to be endothermic. The enthalpy change there would be positive overall because energy had to go in overall. Some reactions, though, take less energy to break apart the reactants than is released when new bonds form as a product is created from the reactants. In that case, if the energy coming out of the reaction, the stuff coming out of the reaction is more than what went in, the overall enthalpy change or the overall heat change would be negative. More was released than was taken in. Why? Why is it that some reactions release energy and other chemical reactions overall take in energy? It's because there's a trade-off. When the heat is released, what we know is the products are more chemically stable than the reactants. What that means is to break the bonds of the reactants may have not required that much energy. Why? Because the bonds were not super strong and they were easy to break. And when new bonds formed for the products, the new bonds could be really strong because they're stable. So when we improve the stability, when the reactants are less stable than the products we make, overall, energy would be released. So the trade-off, if energy is released, if energy goes down, released, stability goes up. If the stability of the products is less than the stability of the reactants, in other words, the reactants were very stable, we broke them apart. The new bonds that formed in the creation of the product were not as stable. Energy goes up. The products are less stable than the reactants. That's what would happen. If the products are less stable than the reactants, the energy would have to go up. So when energy goes up, stability goes down. Why is it that some some chemical reactions could end up producing a product that was less stable? The answer is because there are two driving forces in chemical reactions. There's two driving forces. The overall change in energy or heat, enthalpy, is one of those two. Enthalpy is symbolized, the change in enthalpy is symbolized by a triangle H, H for heat. Enthalpy is the measurement of the change in heat. But the second factor involved in chemical reactions, the second factor that will drive a chemical reaction, is called entropy. So there are two things that drive reactions. The second is entropy. Entropy is the amount of disorder, symbolized by the letter S. So enthalpy is a letter H. Entropy is letter S, and entropy is disorder. Entropy is disorder. Now, in our universe, chemical reactions tend to happen when disorder is increased. What do we mean by disorder? How can a chemical reaction result in disorder? Well, let's say we start with the reactant that is very ordered. Maybe it's a salt with a regular repeating pattern of ions, or maybe it's an enormous molecule, a very, very large molecule, all structured and put together. If that chemical reaction ends up breaking that molecule into smaller pieces, we've created disorder. A big molecule decomposing chemically into smaller molecules where chunks of the molecule are breaking off and going off as the product. That would increase the disorder. And if you think about it, the more things you have, the more the disorder you have. Think about babysitting. Maybe you are a babysitter and you go over to a house and you're scheduled to babysit your neighbor's kids. And you go over and the neighbors have two kids. And you go over and you knock on the door and they're like, oh, thank you for coming. We're going out tonight. Here's our phone numbers and so forth. Call us. And you look inside the house and you don't see two kids there, but you see 22 kids there instead of two. And then you see a bunch of other couples coming out of the house and the couples are like, thanks for watching our kids too. And everyone's like, oh, well, we just thought we would get one babysitter for all these kids. One babysitter trying to manage 22 kids, that could cause disorder. Lots of small things have more disorder than one thing. Another thing, what state of matter a substance is affects entropy. Solids are very ordered, especially salts. Positive ion, negative ion, positive ion, negative ion, positive ion. They're all ordered. Nice, neat structure. They're held in place rigidly. They cannot move. Well, if that is compared to a gas, gases, molecules are bouncing around them randomly, going wherever they want to go. They're just bouncing around randomly. That's much more disorder. A disordered system is said to have high entropy. Ordered systems have low entropy. Chemical reactions happen when they increase entropy. So if a chemical reaction causes disorder, that's a reaction that will tend to want to happen. So reactions where big molecules fall apart into smaller ones, that would tend to happen. Chemical reactions that start with solids and end up making liquids or gases, that would increase the entropy. So the two forces are this, enthalpy and entropy. With regards to the universe, chemical reactions happen that tend to release energy. Exothermic reactions are the ones that try to happen. They are driven to happen. Exothermic. Why? Energy went down, stability goes up. In our universe, chemical reactions are trying to result in more stable compounds having lower overall energy, releasing that energy, exothermic. Those are the chemical reactions that want to happen. If that chemical reaction is able to release energy, have a negative enthalpy, a negative delta H, and that chemical reaction causes greater disorder, that reaction would be considered to be spontaneous. Like chemical reactions that are going to happen. You just get them started and they're going to continue happening. They happen if they have a negative delta H, they release heat energy, and they increase entropy. What about the chemical reactions that do not release energy and have a negative delta H or negative enthalpy? What about the reactions that are endothermic? Chemical reactions that are endothermic are pulling in energy. They're pulling in energy. They're taking in energy. Energy is going up, stability is going down. In our universe, those don't want to happen. So why do they? More than likely, they're increasing entropy. So when one of these is not wanting to happen and the reaction takes place, the other one is probably happening. Enthalpy and entropy. In our next video, we're going to take a closer look at enthalpy, energy changes in chemical reactions. Thank you for watching.